Okay, so in this lecture, we discuss a few important characterizations of finite dimension and non-linear spaces. So, let me just read the topic: finite dimensional non-linear spaces. Okay. Okay. So we just give a quick recall what are non-linear spaces and what do we mean by it being finite dimensional. So the concept relies over what we call a topological vector space. So suppose we have a vector space V. Okay, let V be a vector space, and uh, let the underlying field be the reals or the complexes over R or C. Okay, what we try to do is that we try to uh, induce a topology on V, or we want to equip V with a topology which is Hausdorff, which is Hausdorff, which is Hausdorff, and we are concerned about a map defined on this vector space V, which is given in a sort. For example, let's say we take xy on V cross V, which gets mapped to x plus y, and this is also an element of V for all x, y, and V. And we choose an element alpha from the field, from the underlying field, and we choose a vector from x. That is, it's an element from f cross V. F is obviously R or C. This gets mapped to alpha x. Okay, and this is also in V. This happens for all alpha in F and for all x in. Yeah. This mapping should be continuous. These two mappings should be continuous. So, what are the properties we have? So we have a vector space, and we uh, consider this vector space over field R or C, over reals or the complexes. We try to equip V with a topology, which is Hausdorff. I assume you people know what a Hausdorff topology is. Let me just give a quick picture. Suppose X is a Hausdorff space. Suppose X is a Hausdorff space. Then, if you choose any two distinct points from X, then there exists open neighborhoods of X and Y which are disjoint. Okay. So this is the concept of a Hausdorff topology. So yeah, so we have a vector space over reals or the complexes. We try to equip this with a topology, which is a Hausdorff topology, and we have two mappings which map x and y to x plus y, alpha time alpha and x to alpha x, and these two functions are continuous. So a structure which obeys all these properties is called a topological vector space. It's called a topological vector space. Yeah. Okay. And an example under this topological vector space is a normed linear space. So an example is a normed linear space. Okay. What is a normed linear space? We take a vector space B. B is a vector space, and we define a function on B. We define a function on B. We define like this. So this is a function from V to R, and how do we construct this function? Number one, that this is a positive definite you can even call it a positive definite quantity. So norm of x, we call this function to be a norm. So norm of x for any vector you choose, it's always greater than or equal to 0, and the norm of x is 0 if and only if the vector itself is 0. Okay. This is the first property. It's also called the positive definiteness property. Number two, you have the property of scalar multiplication, that the norm of alpha times x is same as mod of alpha times norm of x. Okay, where alpha is obviously the scalar, that is an element from the underlying field, because V is obviously a vector space. Again, the vector space is R or C. Okay, and number three is that it obeys the triangle inequality, that is norm of x plus y is less than equals to norm of x plus norm of y. Clear? So is it a topological vector space? It's very easy to find that it's a topological vector space. Why is it so? Okay. Observe that we can define a metric on V as norm of x minus y. Observe that this is a well defined. I hope you guys know what a metric defined on our space is, or what a metric space is. It's a well defined metric. Hence, V is a metric space, right? Because if V is a non-linear space, that is we can define a mapping this on V, which obeys these three properties. So I've miswriting it here. So in this case, we say V along with this function is called a non-linear space. Okay. Yeah. So we can define a metric on V using this norm. If it's a metric, we know metric spaces are Hausdorff topological spaces, right? So this means V is a Hausdorff topological space. Hausdorff topological space. So it is a vector space, and it is endowed with a Hausdorff topology. First two properties are clear. Now we are just concerned about the fact whether the mapping which maps x plus y, which maps xy to x plus y, whether the mapping is continuous or not. And that is also pretty easy to check. Why is it so? We use the sequential criteria for continuity in this case. So we are concerned about checking about this mapping only, nothing else. It's very obvious from here. Suppose you choose a sequence xn in V and yn in V. Let xn yn be sequences in V, such that xn converges to x and yn converges to y. Okay, clear? What are we concerned about showing? We are concerned about showing that norm of, or I can think of it as that we are concerned about, since we are concerned about sequential criteria, we are concerned about showing that xn plus yn this converges to x plus y. Okay, clear? And if this convergence happens under this given norm, then we can say that the mapping which takes xy to x plus y is a continuous mapping. Right? Now, what is convergence under a norm? So it's very obvious to observe. You can relate this with the modulus definition, delta epsilon definition in terms of the real analysis. That is, this typically means for all epsilon greater than 0, there exists a delta greater than 0, such that whenever xn, we are talking about sequences, right? We are not talking about arbitrary limits. So there exists an n naught in n, such that whenever n is greater than equal to n naught, norm of xn minus x is less than epsilon. Or you can also think about this as for all n greater than equal to n naught, or let me say in terms of limits, you can also think about this as norm of xn minus x. This tends to 0 as n tends to infinity. Okay, this is simply the definition of convergence of a sequence in terms of a norm. And then let us check this out. Okay, so if I imply this definition, so this is suppose 1, this is suppose 2. So if I imply this definition to 1, what do we get? Norm of xn minus x tends to 0 as n tends to infinity. We are not writing that explicitly. Number 2, so we have here yn minus y tending to 0. What can we say about norm of xn plus yn minus x plus y? We have to show that this tends to 0. That's quite obvious, because we can write this as norm of xn minus x plus norm of yn minus y. Write it like this, and then we can use the triangle inequality. So this becomes norm of xn minus x and this becomes norm of yn minus y. So this tends to 0, this tends to 0 from here, sorry, from here, and that implies this tends to 0. So therefore, xn this also tends to 0. Right. I hope it's clear. Similarly, you can show about the scalar part, that if you choose a mapping which takes uh, alpha and x to alpha x, that's also continuous. You can just choose a sequence like this, and you can check whether alpha xn converges to alpha x or not. That's pretty obvious from the second definition of norm, that is scalar multiplication, a property of norm. So basically, a norm-linear space is a topological vector space. Okay, and since it is constructed upon a vector space, hence we can talk about it being finite dimension. So a finite dimension vector space is a vector space which has a finite basis. That is, it has a finite set of linearly independent elements which span the set. Okay. These topics are very obvious from a course in linear algebra. Right. So we are concerned about some properties regarding finite dimensional norm-linear space. Okay. So let's check. Now, before moving on to finite dimensional norm-linear spaces, we first require a lemma, which is very important in proving the properties. The lemma is very obvious, or I shouldn't say it's very obvious, but it's very important in this case. The property says that let X be a norm-linear space, and let x1, x2 till xn be a linearly independent set, of elements from X. Okay. Then there exists a positive number C such that for all alpha 1, alpha 2, which are scalars, alpha n, for all scalars alpha 1 till alpha n, the norm of alpha 1 x1, that is the norm of the linear combination of these elements x1 till xn, this is greater than equal to C times summation over I equals to 1 to n mod of these scalars. Okay. Or you can also write this in shorthand notation as well. Then summation I equals to 1 to n. Okay, so the norm of this alpha I x. Okay, so this is the precise property. Okay. We will make use of this, so we name this as lemma 1. Okay. We will be constantly using this. Okay. So the first thing which we want to state is that every norm over a finite dimensional non-linear space, so it's a finite dimensional non-linear space, is equivalent. What do we mean by two norms being equivalent? Let me give you the mathematical structure or mathematical statement for two norms being equivalent, and let me give the mathematical what can I say? What term can I use? There's a mathematical aspect behind the word equivalent. Suppose you have a norm-linear space X which has two norms. So let X be a norm-linear space which is this norm. Let X again be a norm-linear space with respect to this norm. Okay. This can obviously happen, right? Because the norm which we are inducing on a given vector space is what we are doing it, right? It's a manual input. This norm, the definition of norm is completely dependent upon us. So we can choose a single vector space and we can imply two different functions, two different norms on that vector space and check whether it's a norm linear space or not. And that's quite obvious. We can imply multiple norms on a single vector space, whatever. For example, let me just give a brief example. For example, if you consider Rn, where the n tuples of R, then you can induce two norms on it. One is called the standard norm. So the standard norm of X is typically the sum of the modulus of each component. Okay. And then you have the two norm, which is the summation of the squares of each component and the square root of the whole set. Okay. Okay. That is, suppose we choose x equals to x1, x2. Let us consider R2. So what is the norm 1 of x? So this is mod of x1 plus mod of x2. And what is the 2 norm of x? It is x1 mod of x1 squared plus mod of x2 squared whole to the power 1. These two are well defined norms on R2. Like these two are well defined norms on RL. Okay. Whatever. So we have two norms defined on X. Both of them are said to be equivalent if there exists a positive number alpha beta greater than 0, such that suppose alpha times norm of norm 1 of x is less than equal to norm 2 of x is less than equals to beta times norm 1 of x. Again, this norm 1 and this norm 2 are specifically symbols to denote that these two are two distinct norms. They have nothing to do with the norm we have defined like this. Here also I have used 1 and 2 just to define that these two are two different norms, nothing else. Okay. You can also have a statement in where you write interchange norm of x, norm 1 of x with norm 2 of x. Either way it's true. So alpha times norm 1 of x is less than equals to norm 2 of x less than equals to beta times norm 1 of x. In this case, we say the norm 1 and norm 2 are equivalent if this happens for all vector sets. Okay. And what is the mathematical point of view of it? Equivalent norms induce the same topological structure. They induce the same topological structure. For example, if you have two equivalent norms over a single nonlinear space, then a sequence which is Cauchy with respect to one of the norms will also be Cauchy with respect to the other norm. That is, if norm 1 and norm 2 are equivalent in this case, and which is a sequence xn from x which is Cauchy under this norm 1, then it will also be Cauchy under norm 2. And the Cauchiness of a sequence of in a finite time in a nonlinear space is exactly same as we just replace the modulus with norm in case of convergence. And a sequence is said to be Cauchy if norm of xn minus xm tends to 0. Yeah. Whatever. Okay. So every norm over a finite dimensional nonlinear space is equivalent. Let us prove this. Okay. So since it is a finite dimensional nonlinear space, we can talk about the basis of it. Let X be a finite dimensional nonlinear space, and let E1, E2 till En be a basis of X. Clearly, X is having dimension n. Now, this set is a linearly independent set, so we can use lemma 1. Right? We will use it later. So, we define two norms on X. Let norm 1 and norm 2 be two distinct norms on X. Be two distinct norms on X. Okay. Now, any element you choose from X, it's a linear combination of these basis elements. Now, for all X in X, there exist scalars, say x1, x2, xn, such that X is written as x1 e1 plus x2 e2 and so on till xn. Okay. Clear? Okay. Then what can we say about the norm of X? What is norm of X? So it's norm of x1 e1 and so on till xn. But each xi is a scalar. We can obviously use the triangle inequality in this case. Right? Let's not do it first. what we can do is yeah, you can use lemma 1 here. So this can be treated as greater than equal to c times summation I is equals to 1 to n mod of xi from lemma 1. From lemma 1 for some c greater than c. Clear? Okay. So from here we can say that summation I is equals to 1 to n of mod of xi, this is less than equals to 1 by c times norm x, right? Okay. Now, now, what is norm 2 of x? Okay, I am using here norm, the first norm, the one norm. I am using the one norm. Okay. Now, what can we say about the two norm of x? So this is again similar to x1 e1 and so on till xn en. We use the triangle inequality in this case. So this is less than equals to. So it becomes summation I is equals to 1 to n norm of xi ei, but each xi is a scalar, right? So we can use the second property, that is it becomes mod of xi times norm of ei, right? Norm of ei 2. Yeah, we are using the 2 norm. Okay. But we have a finite number of elements here, these vectors. So let k be the maximum or the norms of these elements. Maximum of the norms of eis, I is equals to 1 to 1. Okay. Then norm of 2 norm of x, this is less than equals to, so we can replace this by k, right? So it's k times summation I is equals to 1 to n mod of x, right? But we already have here that mod of xi is less than equals to 1 by c times norm x1. So this is further less than equals to k times 1 by c norm of x1. So this is k by c norm of x1, right? Right. So we can choose this k by c to be beta. Let k by c to be beta. Obviously k is greater than 0, right? K is greater than equal to 0. Now we are talking about the maximum of certain finite number of norms. C is also chosen to be greater than 0, so it's k by c is a well-defined quantity. Whatever, let k by c be equal to beta. Therefore, the 2 norm of x is less than equals to beta times 2 norm of 1 norm of x. Now, obviously, whatever steps we had here, we could have interchanged the roles of the norm 1 and norm 2. Right? There could have been, so whatever we did here, it was without loss of generality. Right? So interchanging norm 1 and norm 2 in the above set of statements, so we obviously get some alpha dash greater than 0, such that norm of x1 is less than equals to alpha dash times norm of x2, right? But then we can put alpha dash to the left, so we can say that is 1 upon alpha dash times norm of x1 is less than equals to norm of x2. Norm 2x, not norm of x2, norm 2x. We can choose this 1 upon alpha dash to be alpha, so it's alpha times norm of x1. Norm 1 of x is less than equals to norm 2 of x. Right. So this is one thing we got. This is one thing we got. Both of these imply that alpha times norm of x1 is less than equals to 2 norm of x, less than equals to beta times 2 norm of x. Sorry, 1 norm of x. And this is the exact definition of an equivalent. I guess it's clear. Okay. Next thing is that every finite dimensional normed linear space is a Banach space. What is a Banach space? It's a complete normed linear space. Okay. Number 2. Every finite dimensional normed linear space is a Banach space. is a Banach space. What is a Banach space? So it's a complete. Let me just change the color. Okay. It's a complete non-linear space. What is a complete non-linear space? So Cauchy sequences are convergent. Like we know, not in every topological space, it's not mandatory that Cauchy sequences are convergent. Convergent sequences are always Cauchy, but Cauchy sequences need not be convergent. If you have a certain metric space in which Cauchy sequences are convergent as well, such metric spaces are called complete metric spaces, and the definition comes from there as well. So a complete nonlinear space is a space in which Cauchy sequences are convergent. So we need to show that every finite dimension nonlinear space is a Banach space. It's already given to be a non-linear space, so it's sufficient to show that if we choose a Cauchy sequence from this space, then it's convergent. That is all what we need to show. Okay. So let X be a finite dimensional non-linear space. Okay. And what we need to do, we need to consider a Cauchy sequence from X. Okay. So let Ym be a Cauchy sequence in X. Be a Cauchy sequence in X, and if it's a finite dimension non-linear space, we can talk about its basis. And let E1, E2 till En be a basis for X. Be a basis for X. Now, each of the elements in this sequence are elements from X. So they are obvious. So each of the elements in the sequence are some linear combination of these basis elements. Therefore, there exist scalars which are dependent upon this index M. So we consider these scalars as so this forms another sequence, right? So let this be alpha Im. Alpha Im such that each Ym is a linear combination of these scalars. So it's I equals to 1 to n alpha Im Ei. Okay. Now Ym is Cauchy. Since Ym is Cauchy, by definition, so by the definition of a Cauchy sequence, you will also get the definition of a Cauchy sequence here only. By definition, for all epsilon greater than 0, there exists a natural number n naught such that whenever n and m are greater than or equal to n naught, what happens? Oh, sorry, we have used n already as a dimension. We cannot use it. Let's say r and m are greater than or equal to n naught. Then we have a norm of ym minus yr to be less than epsilon. Is it clear? But what is norm of what is ym? Ym is represented in this way. So yr will also be represented in this way. So this typically implies norm of summation I is equals to 1 to n. So this is alpha Im and this is minus alpha IR, taking EI is common, times EI. This is less than epsilon. I guess it's clear. But this is greater than or equal to, okay, from lemma 1, there exists a C greater than 0 such that norm of summation I is equals to 1 to n, because these are scalars as well, right? Alpha Im minus alpha IR times EI. This is greater than or equal to C times summation I is equals to 1 to n alpha Im minus alpha IR, the modulus of this, right? So suppose this is named to be 2. Therefore, 2 implies C times summation I is equals to 1 to n mod of alpha Im mod of alpha IR minus alpha IR. So this is less than epsilon, right? So we can just pull C to the other side, right? So let me just do it in this step as only. So just putting C. So this is less than alpha by C. But each of these are non-negative terms, right? So this implies, so we can just talk about this inequality for a single term, for some fixed type. This implies that mod of alpha Im minus alpha I r. This is less than epsilon by c for some fixed I. Obviously, the range of I is 1 to n. But this immediately implies that alpha I m, this is a Cauchy sequence again, right? This is a Cauchy sequence of scalars. This is a Cauchy sequence of scalars. From where do these scalars come? They come from R or C, right? We are using here modulus, so we are considering uh, the norm which we had used in example here, right? So we are considering talking about this norm. You carefully observe. So sorry, not the norm. Yeah, wait a second. Yeah, this norm, right? This norm is also called the standard norm. Okay. So I'm just write a quick point out here that R with respect to this norm is a Banach space where this uh, norm of x is simply mod of x. This is the called the standard norm. This is called the standard norm. Okay. Yeah. So this is a Cauchy sequence of scalars. This might be in R or C. So a standard norm in equivalent to the complex field. Let me also denote that as well. C with respect to the norm. So in this case, it's called the Euclidean norm. So in this case, what happens? The norm of z is the absolute value of the complex number z, which you know is root over of x square plus y square, where z was x plus I. So in both these cases, this and this are Banach spaces. They are complete spaces. Now since alpha im is a Cauchy sequence of scalars, they are so this is a Cauchy sequence in the standard norm R or the Euclidean norm C. So this implies, so it's a convergent sequence. It's convergent. The underlying field is always Banach. Okay. So it's convergent. Yeah. So if it's convergent, let us consider a limit of it. Okay, so it's convergent for each I. For each I. Okay. So let alpha im be convergent to alpha I. And obviously I ranges from 1 to 1. Then if y is chosen to be summation I is equals to 1 to n alpha I ei, then first of all y is clearly in x because it's a linear combination of the elements ei, and this is very easy to observe that the sequence ym, which was summation I is equals to 1 to n alpha im ei, this will tend to summation I is equals to 1 to n alpha I ei, where as m tends to infinity, and this is nothing but 1. So ym converges to y inside x because y is an element of x, so this implies ym is convergent in x, and this implies x is complete. Hence a Banach space. Clear? Yeah. Okay. So in this lecture, we discussed two important categorizations of non-linear spaces. I shouldn't use the word categorization yet now, because now what we have done are two important properties of finite dimensional spaces. The next lecture, we will study some important categorizations of non-linear spaces, finite dimensional non-linear spaces. For example, in a finite dimensional non-linear space, a subset is compact if and only if it's closed and bounded. Then in a non-linear space is a finite dimensional if and only if the closed unit ball defined in that non-linear space is compact. Then we also have that a non-linear space is finite dimensional if it's locally compact. Okay. We have certain properties like that. We will discuss those in the next lecture.